Okay, so in this section of the introductory lectures to advanced experimental techniques, we're going to discuss noise, why we have noise, where it comes from, and also what we might be able to do about it. Okay, so we're going to start off with an introduction to noise, particularly its sort of origins in radio and how that then has come about. The second part of the lectures will concentrate on types of noise, the origins of it, explore some of the common sources of noise that you find in experimental physics. The third part will talk a little bit about ways you might be able to go and deal with noise, how to identify where it's coming from, what you might be able to go and do about it, things you need to think about when you're designing experimental apparatus to minimize the effect of noise. And then finally, we'll conclude by looking at some of the value you actually get by not just trying to get rid of the noise, but actually studying it and understanding what it's telling you about the experiments you're doing. So this first part then is an introduction to noise and its origins in the study of the radio. So a lot of the terminology we use in noise comes from its origins in the radio industry. And that's because this additional unwanted interference from other signals in a radio system literally is noise in the background. And so that's why we call this sort of interference with unwanted and unpredictable signals is given the term noise. So in a typical radio receiver, what you're trying to do is pick up some broadcast carrier radio wave, which is being modulated in some way, maybe by its amplitude or being modulated in the frequency. And then you feed that signal through a suitable resonator circuit, which will then deconvolve the carrier wave and the modulation signal. And then the modulation signal is what you amplify and put through your speakers, your headphone, or whatever else it is. I mean, of course, these days, almost all radio is broadcast to digital broadcasts. And so there's an additional stage of converting the carried signal, the desired signal you're interested in, and then processing it digitally to recombine it back in or reconstruct it into an audio signal. But at its origins, it's as simple as saying we have a carrier and we have some kind of desired signal we're trying to pick up. The problem is that our receivers always end up adding some additional unwanted signal into the signal that we're trying to deconvolve to get our desired signal out from the carrier. And even the most perfect radio equipment you could build would still intrinsically introduce additional unwanted signals. And when you deconvolve out the carried signal, that appears as a background hiss or crackle on the back of the signal. And this additional signals, even if you don't have anything else going on, is coming about from thermal noise that happens in the circuit, in the amplifiers. So it's noise being introduced in the receiver as electrical noise, which you're then hearing, and that's sort of characterized by a background hiss that appears across at all frequencies. And we'll explore a bit later about why we get that. However, the problem is in the real world, you're obviously trying to pick up a radio signal that's being broadcast from somewhere, and what you get is not just the noise coming from your detector, from your receiver, but you also get a series of additional signals, spikes, and other features which again are being picked up by your receiver, coming from events in the atmosphere. So the most likely things going on are various electrical discharge events in the atmosphere, of which lightning and thunderstorms are the most common examples. And the problem is that something like a lightning strike is going to generate unwanted signal at pretty much every single frequency you can imagine. And that's because you get a sharp spike event. And then to understand what frequencies that's going to interact with, you have to take its Fourier transform. And if you take the Fourier transform of a sharp delta function, then it has components that exist at all frequencies. And so things like lightning strikes go and give you a interference at all frequencies. So the chart on the screen here shows the sort of typical noise level of an atmosphere, just intrinsically in the atmosphere. And the blue shaded region is the sort of noise levels you get as a function of frequency, just on a kind of calm spring morning. So we're not even talking about a particularly stormy point, which obviously it would be worse. So we do see, however, that our atmosphere is in fact relatively transparent to electromagnetic waves in the megahertz range, which is why we broadcast radio there. So it's not being absorbed, but it still has noise sources in it. And so you've got intrinsically some amount of crackle going on. And then, of course, you have to worry about other sources of noise there. So principally what you might be worried about in a radio receiver is the fact that it's all very well that you're listening to one particular frequency trying to pick up the transmission there, but there are other frequencies in use, and you get certain amounts of spillover from signals being broadcast at adjacent frequencies. So in pretty much across the world, the radio spectrum or the electromagnetic spectrum is divided up and reserved for various uses, much to the annoyance of radio astronomers, because it means that you've got a lot of interference. You only have very limited windows in which you can actually work. But the sort of who gets to use which part of the spectrum is generally controlled by the various governments, and in the Western world, this is generally done by the government auctioning off the rights to broadcast in one particular part of the spectrum. So the chart here shows you the radio spectrum for the United States, and all those coloured blocks are where the signal's been reserved for one use or another use by different applications. And so at the lower frequency range of that, you tend to have sort of military applications, military communications going on, and then as you go through the radio spectrum, you get up to the higher frequencies, you get into the range of various domestic and broadcasting, and you also mixed in there will have various wireless communications technologies, and it just all gets very, 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 very crowded. And particularly where you get to the point of the sort of domestic radio transmissions, then you have multiple overlapping signals, which of course we know about because you can find that if you're listening to one radio station, particularly say if you're in a car, as you move around in the car, then you find yourself picking up some other radio station, or at least you get interference from the radio stations. So man-made signal sources are also a huge problem of interference, even without worrying about atmospheric effects. And then, of course, you get other things where you get unintentional artificial interference. So if you have, for example, a motor that is sparking slightly as the brushes rotate around inside the motor as it drives, you get those little arcs. Well, that's like having a series of little lightning storms going off next door to you. And of course, that gives huge amounts of interference. And if you get other processes going on which are going to involve sudden changes in electric fields, then you see those as interference in your signal. So there's a huge range of potential sources here. So putting it all together, what you end up with when you're doing an experiment, and okay, we've been talking about a radio experiment, but the thing you've got to appreciate is that a radio, in a sense, is deliberately trying to pick up electromagnetic radiation from the environment, but actually any sensitive electronic measurement is going to have a certain amount of pickup of signals from electromagnetic radiation around in the environment in which you're doing that experiment. So you might be deliberately trying to tune into radio, but or you might not be, but you're always going to end up having some level of interference. And this gives you basically a limit of the signal that you can detect. So there's what's called a noise floor, which is the point at which you can't detect a smaller signal because it's lost in whatever level of interference you have in your experiment. However, it comes to, sometimes you can actually realize that you can actually make use of what's going on in the terms of interference. We'll cover more of this later, but just as a first example, This was an early radio astronomy experiment, or it really is the founding of radio astronomy, because it wasn't trying to be a radio astronomy experiment. It just turned out by accident to be a radio astronomy experiment. So this was an experiment done by Karl Jansky, where he was trying to see if he could make a directional radar locator. So he was trying to see if he could locate a particular radio source on the surface of the Earth. The idea that this might be useful for tracking objects on the surface of the Earth. So he built a rotating radio detector and was trying to identify if he could locate a radio source. Of course, the first thing you do is you just spin it around without a radio source there to go and see that it gives you a more or less constant level, irrespective of the direction. And unfortunately, that's not what happened. As he spun his detector around, he saw that he got extra noise in certain directions. So that implied that he was picking up some kind of noise located somewhere. The problem was that what he was picking up didn't seem to be related to anything that was actually on the surface of the Earth. So by moving his detector around and repeating the experiment, he was able to show that it didn't relate to anything that was on the surface of the Earth. And by doing it at different times, he was able to show it didn't even relate to anything in the solar system, because it didn't change as the Earth went around the sun. Turns out what he's actually picking up is a radio source that's at the center of the Milky Way. So for the first time, he was identifying that the center of the Milky Way has a very intense radio source there. And so, in fact, this was, if you like, the birth of radio astronomy as a branch of astronomy, was this idea that you could actually use radio detectors to pick up remote sources from the night sky. And of course, being radio waves, you don't have to wait for the night, you can do it during the daytime as well. This is kind of a nice example showing that by paying attention to noise and trying to think about where noise comes from and what it means, you sometimes go and detect additional science.